Hi everybody. Today I'm going to present you our work entitled Mechanical Properties Prediction of 2D Interlocking Structures using Deep Learning Methods. First of all, I'd like to summarize the main points I'll be touching during this presentation. So a brief introduction on the background, so interlocking features and why they're important in some biological systems, and deep learning methods. Then I'll be talking about the geometry and the database generation that we made for training our deep learning model. Then some details on the finite element and deep learning model and approach. And finally, some results and conclusion. But why are interlocking features important? So here is just an example from a paper of Jesus Rivera, where the authors found out that the peculiar feature of interlocking, as you can see here in the inset, can give to the specific species of beetle a remarkable property. Specifically, the authors proved that together with the composite material, with fibers, reinforced material, and with an interlocking features like inspired by the beetle, such joint can reach high energy and is much tougher than the classical joints present in aeronautical field, but having about the same strength. So this is just an example of a biological system with these specific interlocking features, but there are other scientific evidences where the interlocking microstructure provides remarkable mechanical properties. For example, the walnut shell has a 3D interlocked structure which provides greater stiffness and toughness to such microstructures compared to other rigid plants. So the deep learning, why did we choose to use the deep learning to predict such mechanical properties? Well, we need to overcome the computational cost of numerical simulations, and specifically in case of 2D interlocking structures or even 3D, we are dealing with high nonlinear problems like contact, plasticity, and damage initiation evolution and crack propagation. And we want to quickly and accurately predict the mechanical properties of such structures and use such models, deep learning models, as a surrogate for predicting these properties. Here in the image we see two examples from a paper of Jan LeCun in Nature Review of a deep feed-forward neural network scheme and a convolutional neural network. So deep learning can be considered as a branch of machine learning where mainly networks are made of many hidden layers. You can see here just a scheme with two hidden layers, which can learn abstract representation of the information present in the input, and the network can can recognize, can predict a structural property relationship, as in our case, and what we leveraged was, in our work, a convolutional neural networks, since we are dealing with images, so we are representing our geometries as images, and convolutional neural networks are the best suited networks for dealing with images. So deep learning methods and models have been used widely in solid mechanics and material science. Here we have just two examples. The first one is an example from a paper where the authors wanted to, and succeeded in that, to homogenize and 3D binary composite, RBE, as you can see here, made of two faces, the black and the gray, to obtain as an output the stiffness of such material. Another example that I reported here is from a paper of Grace Gu, where the authors prove that machine learning algorithm can be used also for inverse design of materials and to design fracture-resistant composites, for example. So in our paper, what we did was to create, first of all, the interlocking geometry, and for that we use, as you can see here, a flowchart of the brute force algorithm. So the geometries we are dealing with are kind of these 2D geometries, so you can see here in the box, and where we have two faces, the gray and the black, and we have just interlocking between the two faces, neither with the soft tissue between the two faces, nor with some adhesive bonds, but just interlocking. So this is a scheme of generation. For the generation of the geometries, we start from a matrix, from an n by n matrix with the first row full of black building blocks. Then we permutate the second row, and then we apply growth rules in a cellular automaton-like style, let's say. But the growth rules are applied row by row and element by element. Other constraints that we applied during the brute force algorithm were the volume fraction, which is the volume of one cell of the black or the gray with respect to the total volume. And then we checked at every step also the presence of mechanical interlocking. And finally, we checked also for path continuity that I will be explaining you in some seconds. So the growth rules, we divided the growth rules in boundary growth rules and the inner growth rules. To generate a database of geometries to train our network, we chose to parameterize the whole set of possible rules, as you can see here in these images. And so, therefore, for each permutation of the second row, we have every possible rule applied, and the ones which satisfy our constraints are taken as geometries for the database. So here you can see it's worth to note two examples of path continuity violation. So you can see here that going from one black cell to this other one, we need to cross the gray face, which is a violation of the path continuity constraint. And then, so we chose to create two databases. The one is the first one is a 10 by 10 design space, and the second one 20 by 20. So for the first one, we generated all the combinations by the brute force algorithm, about 18,000 half geometries. While for the second one, we randomly sampled about 3,000 interlock configurations from the whole combinations. And then we split it in the training, validation, test data for training the deep learning model and to assess its performances. So about the fat element model, here you can see a scheme of the geometry of one example with specific boundary conditions. So we have applied uniaxial tensile loading, and we constrain, as you can see, the left and the right edge along the x direction. Here you can see some details about the model, but it's worth to note that we have a plasticity model and damage initiation and evolution together with contact, which makes the model and which gives to the model high nonlinearities. And then we extract the stress strain, we deduce the stress strain curves, and from those curves we obtain the mechanical properties. We consider two properties: the stiffness or effective elastic modulus as the slope of the initial linear part. We consider the strength as the peak of the stress strain curve, and then the toughness defined as the area underneath the curve. Some details about the deep learning model. So here you can see a scheme of the deep learning model. So we have as input the one image which represents the geometry, the interlocked geometry, and then some convolutional blocks which are made of convolutional layers together with average pooling layers and batch normalization layers. And then finally, a fully connected layers which predict the mechanical properties as output. So here you can find some details about the deep learning model and some together with the metrics that we chose to use for evaluating the performances. It's important to highlight the figure C and D, where we have a set of images from shallow layers in figure C and from deeper layers in figure D. You can understand easily that in figure C, the network can learn some features from the geometry, and humans can recognize specific features, geometric features in the images, while in deeper layers, the network learns abstract representation of the information that humans cannot, that are not readable by humans, but they form a useful representation for predicting a nonlinear relationship between the geometry and the mechanical properties, a nonlinear relationship. And finally, we adopted trustful learning approach. So we did prove that pre-training our deep learning model with a dataset from a smaller design space, in this case a 10 by 10, can be used for predicting the mechanical properties of geometries from a larger design space, in this case a 20 by 20, just by showing to the network just few new examples from the larger design space. Some results. So here, to summarize, we have the mechanical properties correlations between the strength, sigma, and stiffness, and the toughness. You can see here. What's important to look at is here we have three geometric parameters that we consider: the interlocking area, which are the here shown in blue, as you can see here, which are the areas where the load is transmitted along one axis. And then we have the lobiness, which is characteristic of cells, for example, pavement cells in leaves, which is a measure of how many lobes are in the cell, and interlocking area. So it's important to say that for the deep learning model, we found the best model. So we optimize our deep learning model, evaluating 24 models as in total for the three mechanical properties, and the parameters that we changed were the number of filters in the convolution layers, the patch size in the convolution layers, and the number of convolutional blocks in the deep learning model. So these are the characteristics, the parameters of the best model that we found after the tuning. And then here you can see other interesting things. So for example, what we did was a training data sensitivity for our deep learning model. So here you see in the y-axis we have three metrics: the relative mean absolute error, the coefficient of determination, and the accuracy for the prediction of the three mechanical properties. So looking at them, we see that adding new training data, the performance increases as expected, but what's it's important to understand is that we need just 20–30% of the training data to obtain high accuracy for the prediction. And then here, just consider this block here, and so you can see that we compare the top 12 performing geometries from the finite element simulations and the top 12 performing geometries from the deep learning model. We did that for the strength and for the toughness. As you can see here from the first row, comparing the finite element results and deep learning results, we see that the deep learning model could predict the pattern in the geometries and that allow for high strength. And the same occurred for the toughness. As you can see here, the deep learning model predicted analogous pattern in the geometries. And finally, these are the transfer learning results. You can see here that this time we have the 3 metrics, as you can see in the y-axis, while in the x-axis we have the training data density, which is this time the new training examples that from the larger design space that we have shown to the network pre-trained on the 10 by 10 design space. And we can see that just adding new examples, you can see here just 40%, 50% of new examples, the accuracy considered and the other metrics improve, and therefore we are able to predict the mechanical properties of 2D interlocking structures using a smaller design space as a training and predicting such properties in larger design spaces. And in conclusion, so for the first time we used deep learning models to study interlocking mechanism and to predict quickly and accurately the mechanical properties of 2D interlocking structures. And more importantly, we are able to enlarge the design space of interlocking structures compared to analytical models, which require simplicity in the geometry, or finite element simulations, which involve high nonlinear problems, therefore high computational costs. And we wish in future applications of deep learning methods to study the remarkable properties of some biological systems, and specifically to design novel interlocked materials. Thanks for your attention, and I hope that you have questions and comments on our work. Thanks again.